Fantastic. Okay. Thank you all for joining today for our SLAM seminar. Today's speaker is Carmen Lee, Dr. Carmen Lee, and it's my great pleasure to introduce her. Carmen Lee is an experimental physicist investigating fluid dynamics and granular physics, currently at North Carolina State University as a postdoctoral researcher in the Department of Physics. She has interest in exploring fundamental principles and interdisciplinary connections in many of these soft matter topics. Her research delves into understanding the behaviors of fluids and granular materials, drawing parallels between physical phenomena and natural systems. And as I said, she is at NCSU as a postdoctoral researcher at the moment. She completed her PhD in physics at McMaster University, focusing on driven flow of droplets and bubbles. And I think today she's going to tell us something about relating microscale to the macro in granular materials. So with that, take it away, Carmen. Thank you again.
Thanks so much. Thanks for the lovely introduction and for having me to give this talk. Today I'm going to tell you a little bit about relating microscale structure in granular materials to their macroscale response. And I know a lot of people here are from different backgrounds, so I'm going to start us off with a very basic intro into what is a granular material. And at its heart, it's a collection of solid macroscopic grains. And kind of the canonical example of a granular material is a pile of sand. But we can go to anything like coffee beans that we roast ourselves, if you're really into that. We can go to bulbs in a children's ball pit, all the way up to boulders on an asteroid. And so what I really want to drive home here is that the grains that make up a granular material vary strongly in their shape, their size, and material. And that means that they can be anything from extremely hard to extremely soft. And not only is the material that they're made out of very diverse, but also are the interactions. So you can imagine if you take these two coffee beans and you rub them past each other, you're going to have friction between those. If we add a little bit of energy to the system by like shaking the coffee beans, we start to get collisions. And then those are for dry grains, but we can add liquid to the system. And if we make that liquid and particle suspension flow, we can add in hydrodynamic forces. If we make the system very small, we can get capillary forces. And then if we make it really dry again, we can get something called tribocharging, where we get electrostatics between the particles. So there's this grand wealth in interactions between between the grains, and that allows us to explore really diverse behaviors. But we can generally categorize these into three main categories. The first being solid. So if we walk on sand on the beach, we know that that sand is going to hold us up. We're not sinking through it. And that's because friction between the grains of sand work together to form a solid surface. However, if we add a little bit of energy into the system, say if we fluidize the sand bed, it can enter a liquid-like behavior where now we have collision and friction. And then if we add even more energy, we can get something that approaches a gaseous material. So you can see this dust cloud here. And if you've ever sandblasted anything before, you know that it's really the collision between the grains that are what is interacting. And I also want to say, feel free to stop with any questions during this talk. I'm happy to answer them as we go. I'd rather you ask them now than be confused later. So those are our kind of main behaviors of a granular material. And something that a lot of folks are really interested in is, when do we change phase? When do we go from a solid to a liquid? And just to give you some examples of this can happen pretty catastrophically in the form of failure. So if you have this is a grain silo shown here, and you can see that the outer banding of the silo has failed. Those grains that were previously acting like a solid are now fluidized. They fall very rapidly, and that can cause a lot of death in agricultural workers. And you can see as well that in some cases we can actually see a gaseous cloud form. On a geologic scale, this can happen in the form of landslides. So this is an example from Mud Creek, which is on the coast in California. And you can see this highway here. This is Highway 1 that passes through, or that the mudslide has hit over. Just to give you a really an idea of the scale of material that's fallen here. A little bit closer to home for me, this is where I grew up. This is a sand dune, and you can see it's been around for quite a while. There's grass that's stabilizing the sand dune, keeping it in place. But after a hurricane came through recently, you could see that there's been drastic change in the landscape. There's been a lot of washout of this dune, and it's no longer as stable. And so something that a lot of geotechnical engineers try to ask is, well, when do we go from solid to liquid, especially in the context of natural disasters? And can we predict when this failure will happen? And this is a huge question, and I am going to answer just a very small part of this question, but it's very interdisciplinary as well. And just to make sure we're on the same page, because I'm going to be talking about these terms quite a bit, I want to make sure we understand what I mean by strength and failure. And really what we're going to talk about first is how we measure stiffness. And this is an easy thing to answer in a bulk material. We can just measure the stress strain response. So if we take this gummy bear here, which we're going to call it a continuous or bulk material, we know that it has a length L0 and a cross-sectional area on top of its head A, and there's a normal vector pointing out at the top. And what we can do is apply a force by giving him a very heavy hat. And we can relate this, we can call that this, we've applied a stress to the system, which is the stress is the force per unit area. You can think of it like a pressure. The other thing that we can do is we can also see that we've compressed this gummy bear by applying this force. And so we can measure that change in length. And by relating the change in length to the original length, we have measured something called the strain. And if we assume that this gummy bear is linearly elastic, we can say that we can measure something called the elastic modulus, which is the ratio of stress to strain. This is a material property. The more stiff the gummy bear, the larger the elastic modulus, and the harder it is to deform. But we can also apply a force not just in the direction of the A vector, but also parallel to it or orthogonal to it. And this is through something called shear. So if we apply a force in the shear direction, we can again measure the deformation. And then again, we can assume that it's linearly elastic, and we can measure the shear modulus, which is called G. And of course, we don't have to apply just the compression or the shear independently. We can apply it at the same time, and we can deform this gummy bear in all kinds of different ways. And so that's something that we can do for a bulk material. We can measure the stress and strain response, and we can relate it back to its material properties. But for a granular material, something like a pile of gummy bears, it gets a little bit more complicated. If we apply it, we could do the same things that we did before. We can apply a load, and we can measure the stress and strain and failure. And then, but this is going to change because this pile of gummy bears is heterogeneous. There's different gummy bears of different sizes. We have air involved. It's nonlinear, which means that we can't assume there's a linear elasticity. We can't just measure the shear modulus or the elastic modulus. And it's also history dependent. So if we prepared these gummy bears in one way and then prepared the gummy bears in a different way, we would get a very different response in the macroscale behavior. And so to really understand what we expect to see in terms of stress and strain, we have to understand the microscale. And by microscale, in this case, I actually mean particle scale. We're well above any micron scale features here. So gummy bears are about 1 centimeter in size. And we're interested in how these particles are in contact with each other and how the forces are distributed through this pile. So you can imagine as we compress the gummy bear pile, some of these gummy bears are going to be squished a lot more than other gummy bears. And some of them are going to be in contact with some, but not others. And those contacts might fluctuate as we compress it further. And so this is like this relationship between the microscale and the macroscale has been studied quite a bit. And we've seen a couple of different things. The first thing was by that I want to show you is the simulation by Boy, where they took a frictionless packing of particles and they brought it to the jamming point, which means their particles aren't able to rearrange past each other. And what they did was measure the shear modulus as a function of the angle that they apply to shear. So they could apply it in the X direction, they could apply it in the Y direction, or they could apply it anywhere in between. And what they found is that the shear modulus is anisotropic. It really depends, how much it resists being sheared depends on what angle you're shearing it at. And so there's this inherent anisotropy. And then the other thing that they found is that they took the same particles, prepared them in nominally the same way, except they had a different packing at the end of the day. They found that the shear modulus changed quite a bit. So we go from, that's where we see the black and the red, which are still anisotropic, but very different from each other. So this tells us that at the contact scale, we really, or to understand the shear modulus, we really need to understand the particles at the contact scale. And just to show you how this affects deformation, in this study by Ellenbrook et al., what they did is take this shear pack, these frictionless particles, and in the top panels here, it's at the jammed state, so the particles aren't able to rearrange. And then the bottom two panels were just below jamming. So there's the rearrangement is allowed by the particles. And so when they compressed it or sheared it, they found that there's this really strong non-affine deformation where the arrows tell us how much each particle has moved. And you can imagine that if we had a different packing, we're going to have very different motion. This
So
also
can I ask a quick question about the graph on the left? Like,
yeah.
so how is the zero defined there? Like, what does negative mean?
I'm actually not sure. That's a good point.
Just an average or like a convention that shows, I assume.
Yeah, I think it's just whatever convention they chose.
Okay, thank you.
Yeah. So along with looking at jammed cases, we can also look at rheological features. So in this study by De Cruz et al., they took a granular packing and they sheared it, and they measured something called the macroscopic friction coefficient. So this is how much the packing as a whole resists moving, just like a regular friction coefficient. And then they plotted this as a function of the inertial number, which you can think of as how fast they made the particles move. And so what you see here is the macroscale friction coefficient for frictional particles with friction above, as well as frictionless particles shown below. And I want to say that even though the particles themselves don't have friction, they can still have a macroscale friction coefficient because you'd have to be able to move one particle through another, and that resists motion. And so what De Cruz et al. Did in this study where they simulated these particles, they looked at all the force distributions. And what they found is that for the normal forces shown on the left or the tangential forces shown on the right, for particles with friction in blue and particles without friction shown in red, regardless, there's still a strong anisotropy in the force distribution. And so maybe the findings by Deguaboy, where they looked at the shear modulus, shouldn't come as a surprise because you see this strong anisotropy at the particle scale. And so the micro to macro conversion has been looked at in a couple of ways in forms of theory. This paper by Eric DeJuly looked at how you can map statistical mechanics to granular material. So trying to make that analogy of the solid to liquid to gas through StatMech. And this was done as well by Ephraim, who I'll show the data for later in this talk. But what I want to say here is that it's actually really difficult to do this experimentally. Most of these data that I showed you are from simulations. And that's because it's really hard to extract out particle scale information. And so what—
Carmen, can I ask a quick question?
Yes.
Here, with all the data that you've shown and all the examples, the anisotropy that you were mentioning, so is this anisotropy, and this is at the particle scale you're saying, but where is the axis coming from? Is it like the shear axis? What's breaking symmetry?
So you can see that there's a strong asymmetry in so they took just a square box and then sheared it this way.
Okay.
So, and I'll talk about why we see this later.
Okay, but there is a correlation of this asymmetry at the contact scale with a macro axis, which is defined by boundary conditions of some kind.
Yes. So
Okay.
in this case, it would be, I think it's going to be 0 is along the plane, and then the 45 degrees is the shear band.
Okay. Okay. All right. Okay.
Yeah. Good
Thank
point. Okay. So we were saying that it's hard to get particle scale information out from anything but simulations. And that's because if you looked at a pile of sand, it'd be difficult to just say, okay, these are where the contacts are and these are where the forces are. So I'm going to show you a system where we can extract that information. And that's in this experiment of photoelastic particles. Next slide, I'm going to tell you about how these work. But for now, I just want you to look at this. This is an annulus or an annular shear cell, sorry. And it's full of these photoelastic particles. And photoelastic particles are cool because they allow us to see the forces being loaded through these particles. And what we're going to do is rotate the inner wheel. So it's acting like essentially a two-dimensional rheometer. And what you can see is as I rotate this, we see these beautiful patterns appear, and these are called force chains. And you can see that as we rotate these forces, the inner wheel, we see these force chains appear and fluctuate and break and then rebuild, and it's quite heterogeneous. And we're just going to let this go for a little bit because it is just so pretty. And so again, this is an experiment. The particles are about 1 centimeter in size, and they're about the squishiness of a pencil eraser. And this video has been sped up by about 25 times. And what's nice about photoelastic particles, or actually before I say this, so this would be the ideal system. Here we can get the macroscale friction in a rheometer context or a rheological context. But it's kind of complicated. It's in polar coordinates. To understand information from it, it takes a little bit more work. So we're going to put this aside for now, and I'm going to turn us to a square system, a nice Cartesian coordinate system. And so what we're going to look at is, can we understand macroscopic friction, which I showed you on the previous slide, but now using particle scale information from experiments. So using photoelastic requires us to understand birefringence. And just as a refresher, birefringent materials are those with 2 indices of refraction, which means that light goes through at different rates, or different speeds rather. And in a photoelastic material, if you stress this material, we change the birefringence. And so if we shine light through a polarizer and it interacts with this photoelastic material while it's being stressed, we're going to see a fringe pattern that shows us where the stress is applied. And just to show you how this changes with increasing stress, I have this photoelastic disc here between a set of pliers. I'm going to apply a stress to it. You see, as we increase the stress, we go through this really beautiful rainbow pattern. And we can solve what this should be for circles. And so what we can do is take these discs and place them on a air bed, essentially. So think of this like a air hockey table, if you've ever played with one of those before. So these particles are floating on the surface. There's no basal friction between the particle and the surface. As I shine light onto the surface, polarized light, and then it reflects back up into our camera. And now we can look top down onto the surface, and we can make a granular packing out of it where we have 2 fixed walls and 2 movable walls. And so this system was taken by Ephraim Billyline, a former undergraduate. He was at Chicago and has now moved on to industry. But what Ephraim did was take these packings of about 900 particles, and then he could load them in different ways. And so actually these data are available in this paper here if you want to play around with it. So what he did was take these packings and compress them uniaxially, and you see these force chain patterns appear, and they're quite linear in this case, or they're quite directional. And then what he did next was compress it biaxially, and you can see that the pattern has changed. We've kind of gone from a more linear feature to more honeycomb shape. And then the last thing that he did was apply a pure shear, where he compressed from one side and expanded from the bottom. And so you can see again, there's quite a strong anisotropy at first, and then it grows. There are two things that I want to tell you about this, is that because these are on kind of an air hockey table, we can expand the box again. The particles will rearrange by themselves, and then we can recompress into forming a new packing. So it's kind of like it erases the previous packing. And then the other thing is that these are done quasi-statically, or statically rather. I'm playing these as a video, but what happened was that Ephraim compressed the packing, took an image, compressed the packing, took an image. And so that means we know that the packing is in force balance. And this is important because what we can do next is take these particles or these images and run them through the photoelastic grain solver. So this is open source code written initially by Jonathan Colmer. I've made some tweaks to it for these data so that we can get all of the really small contacts between the particles. And what we did was take a color image shown like this, where we have two channels. We have red and green. We steal from confocal microscopy. And we can split the image into the red channel, which just looks like circles. And then we can use circle finding to find the particle position and size. And then we also have the green channel, which allows us to see the forces. And we're able to solve for the particle contacts and the forces as well. Taking these data, we're able to reconstruct it just to make sure everything makes sense. And you can see that it does a pretty good job. If they were off, we would see really weird images in the reconstructed forces. So we have particle scale information here. And the next thing that we want to do is to see if we can construct the macroscale stress tensor.
Carmen, another
Yes.
clarification over here.
Mhm.
So if I understand correctly, because birefringence is caused by anisotropies, so do you get, what constraints are there in sort of doing this, in taking the image, the optical output, the optical signal, and in making inferences on the force? Can you get all the components of the force? Can you also get the isotropic part rather than just the shear at the grain level? And
Yeah.
or are there assumptions you make to be able to compute it computationally?
So at the grain level, we have to assume that we've found the location of the stress. So you can see there's like, here there's a contact, there's a contact, and here there's a contact. So a lot of the work that I did was putting into how we can detect whether or not there's a force there.
Okay.
Because these ones are pretty obvious, but as we get to smaller and smaller forces, it becomes harder to tell what's noise and what's force.
Yeah.
So really what we need to know before we can do anything is where the particle contacts are.
I see.
And
Yeah.
then from there, you're able to essentially just squeeze it algorithmically and see how close we can get to the original image.
Okay. And over here, only the size is different, but the material is all the same.
Yes, they're all made out of the same polyurethane plastic.
Okay.
Yeah.
And
Actually, a lot of plastics are photoelastic. So if you've ever been in like a bus stop and you've had polarized sunglasses on, you can sometimes see these stress patterns appear as like beautiful rainbows from like usually the corner.
I see. And the elasticity of the material, which you benchmark separately, is isotropic, or is that also anisotropic?
We assume it's isotropic.
Okay.
But I imagine you could probably make a material that is anisotropically photoelastic.
Okay.
Yeah.
Thank you.
Okay.
Yeah, so one or related question. So do you use like a bidispersed system on purpose because that's better for jamming?
Yeah, we use a bidispersed system to prevent crystallization.
Okay.
So you can imagine if they were all the same size, we would end up with just fracture planes rather than a heterogeneous material.
And another quick question. So what you were saying about the lighting up of the force chain. So is there some sort of thresholding you have to apply that above a certain brightness you consider it like a force, and below that it's a noise, or how do you?
Typically we threshold with the gradient. like how much the gradient and intensity changes over, say, some circle amount. And then if it's above that threshold, it works. And if it's below that, it doesn't. We count it as not a force. But we can get quite sensitive. You can see like some of these very small forces are able to be picked up by the algorithm.
Thank you.
You're welcome. Okay. Any other questions on the experiment? I realize that I'm quite familiar with it because I've thought about this a lot. Okay. So now we have the particle contacts, the vector forces, as well as the position and the size of these particles. So the next thing we can do is start to look at the macroscopic, the macroscale components. So I spoke a little bit before about the stress. And just as a reminder, this is what we do with the gummy bear on the bulk scale. But we are essentially doing the same thing with our box. So if I have my granular packing here like this, I can compress it in two ways. The x direction indicates x compression, the y direction indicates y direction compression. And then we can also apply the shear on our boundaries. So that fills in our diagonals. And we're working in 2 dimensions, so we're keeping a 2-dimensional stress tensor here. As a reminder, back to the gummy bear, we can write the stress as the force per unit area, which we can do here. And then the other thing that we know is that in this granular packing, if we're in equilibrium and everything is force balanced, these forces on our boundaries have to be equal and opposite to the forces on our boundary particles. So if we sum up these forces, they should be equal to the compression or the shear. In the case of the experiments that Ephraim did, we didn't really apply shear to the boundaries, so we won't see much of that. And then if we further force balance, what we can say is that these boundary forces, if we sum them up, have to be equal and opposite to all of the forces inside of our packing. And so really what we can say is that the summation of the forces, we can write this out in our stress tensor. And we can do a little bit better than that. And I'm going to skip a couple of math steps here. And I want you to trust me, is that if we look at these particles, we can see that there's a force that's not in the direction of our normal vector. And we can go ahead and write these particles down as A and B. And we can see that there's a branch vector that goes from the center of the particle to the contact point. And the other thing that we can do is write that the force vector goes from the contact point to wherever it points. And we can essentially rewrite this projection as the summation of the branch vector multiplied by the force vector over normalized by the area of our experiment. So I'm skipping a couple of steps here, but if you break it up into components and then do the cross product, you end up with this, or the outer product, you end up with this, where the I and the J correspond to the XX or YY or XY, etc. And so what we can do is take this granular packing that I showed you before. This is the pure shear case. So we've squished from the X and expanded from the Y. And we can take this summation, do it for all of our data, and we end up with the stress tensor. So this is a little bit complicated, so let me walk you through it. So we have our stress as a function of frame number, and I'm plotting 5 different loading cycles here, so you can see an example. So these are 5 completely different packings that have undergone the same loading. And so we see the blue corresponds to the X compression, the red corresponds to the Y compression, and then the green and the orange, which you can kind of see that they're not quite the same, are our shear. And so you can see that, first of all, that the shears are essentially 0, which makes sense. That's not what we did to the packing. And then in the X direction, we see it's generally largest. That makes sense. We primarily compressed in the X. And then with time, we see that the Y compression grows as well. So what I want you to get out of this is that we can measure the stress tensor from the particle scale information. And we can also see quite a bit of variation depending on which particle packing we did. So then the next thing that we can do is start to pull out some important metrics. The first is the pressure, which is the summation of the two main compressions. And so if we plot the pressure as a function of strain for multiple different loadings, as indicated by the different colors, we see that generally it increases as we increase the strain. That makes sense. The more you strain it, the higher the pressure should be. We can also measure the shear, which is everything else essentially in our stress tensor. Or you can think of the shear as the deformation in our packing. And so the shear as a function of strain also increases as we strain it. That also makes sense. And then what we can do is take the ratio of the two, which the ratio of shear to pressure is actually the macroscopic friction coefficient. And so if we plot that for all of these data as a function of strain, we see that it decreases. And this indicates that we're seeing a strain softening in our granular packing. And this is what we would expect for most granular packings. It should deform less as we've strained it further. And so that's our macroscopic friction coefficient. We can measure that from our data. But that's really all we can do to understand it. For now, everything else is mostly empirical. So what we're going to do is go ahead and start looking at the particle scale.
Carmen, quick question.
Yes.
The strain over here in all three of these plots is always uniaxial?
It's deviatoric. So we have to measure both the X and the Y.
And okay. What were they gonna the different colors are just different packings?
Exactly.
Packing fraction?
Not packing fraction, just different rearrangement of the particles.
Yes, but the packing fraction is kept the same.
Yes. Yeah, it started off at the same area.
And they're all how close or away from jamming are they?
You can see essentially we are approaching jamming. So we end at jamming.
I see. Okay, so this is the shear induced jamming kind of.
Exactly.
Okay.
Yeah.
Okay. I see. Thank you.
You're welcome. Okay, so now we're going to move away from the macroscale measures to now looking at the particle scale measures. And so the first thing that I want to introduce to you is this idea of anisotropy. And we've talked about this in a couple of different contexts before. But the first thing that I want to talk to you about is the anisotropy we can see in the contacts. So in this image down here, you can see that the particles are pretty randomly oriented. And if we were to go through and look at all of the contacts, there should be no preference in direction. So that means that it's an isotropic packing. Compared to this one up here in the top right, where we can see a very strong alignment in the direction of the contacts. You're essentially only going to get a contact in the horizontal direction or in the vertical direction, nowhere else. And then the other two packings show us a variation somewhere between isotropic and perfectly anisotropic. So we can get anisotropy in contacts or in the fabric, as some folks call it, but we can also see it in the forces as well. So these are photoelastic particles that have been isotropically compressed, and you can see the forces generally don't have any directionality to it, especially when in comparison to the shear case, or the pure shear where you compress and expand. You can see that in the shear case, we get this very strong anisotropy towards the horizontal direction. So we can get anisotropy in the forces as well as the contacts. And we want to figure out a way to characterize it. So first of all, I want you to consider an isotropic packing like this. This is just taken from the previous image, but we're going to keep the isotropic packing in mind. And I'm going to flip us to this image because this is what I made the schematic on originally. So keeping in mind all of our contacts, what we're going to start off with is building an angular histogram of these contacts. So if we look at these contacts that fall within this angular wedge, we can count them up and just simply add them to our histogram. And then we can do this again for another section of contacts, and we can do this all the way around. And if it was isotropic, we would expect that it looks like a circle, because there should be no preference in direction for where the contacts appear. The next thing that we can do is, because we have this vector force information, we can look in at these two particles in this that fall in these blue contacts, and we can count the forces. So we can sum up the normal force as a function of contact angle. And if I do this, if it's isotropic, we'd expect that it's just a circle as well. And then, so that would be, in this case, the force, the average force bin by the contact angle. And then, of course, because we have the vector, we can add in the tangential component as well. And in this case, we have to consider if there's going to be clockwise or counterclockwise rotation from our contact. And in the case of an isotropic packing, we expect that it should average out to 0, so we shouldn't get anything. Now I want to contrast this isotropic case with the anisotropic case, where something that looks like this. We'd expect that the contacts are going to be aligned in the horizontal direction. The normal forces should be aligned in the horizontal direction. They don't necessarily have to look exactly the same, but they should follow each other generally in shape. And then in the tangential forces, because in this case it was sheared, we'd expect that there should be a preference in direction. And so what this means is that, say at this orange angle, we'd expect that the majority of those contacts are going to be rotated clockwise. So there'll be a force on it due to the friction of these particles. And then to balance this, we'd have to have a counterclockwise rotation at a different contact angle. And so we have two different distributions here, either the isotropic case or the anisotropic case. And this has been used by a paper by Rothenberg and Bathurst in 1989, where they simulated about 1,000 particles with friction, and they compressed them biaxially. So more strongly in the vertical direction than in the horizontal direction. And then they did the same distribution analysis. They looked at the distribution of contacts, and they fit a Fourier mode to it. They said that the probability of finding a contact should be equal to 1 plus some anisotropic measure multiplied by a cosine of the angle. And so this tells us that the more anisotropic it is, the more peanut-like it should be, or the more elongated it should be. If the anisotropy were 0, we just get a perfect circle. They did the same with the normal forces and expanded it similarly, where they found another anisotropic measure. And they did the same thing with the tangential forces, where, again, they found another anisotropic measure. The interesting thing is that they took these three anisotropies, A sub n, A sub t, and they summed them up, and they found that it should be equal to the macroscopic friction coefficient. And so they called this the stress force fabric relation, where they essentially relate microscale anisotropies to their macroscale friction. And this has been around since 1989 and has yet to be proven with experimental data. And since I have the experimental data, obviously that's what we're going to be testing today. And just to show you that if we take this this approach that they did, there's actually pretty serious tensor analysis behind it. If you take the stress tensor, and then this was done by Lee and Yu in 2013. If you take the stress tensor and expand it and then bin by the angle, which is what you do in the histograms, you can see that it should be equal to the probability of finding the contacts at any given angle multiplied by a vector, contact vector, and a force vector. And then what they did was expand this into these huge expansions of vectors, expanded it further into a Fourier analysis, and then they found that you can indeed actually discard the higher order terms. So Rothenberg and Bathurst's very first order approach is actually relevant here, and it works. So that's good for us. And so the next thing that we can do is see how this works for our data. So I've shown you toy data before, I've shown you simulated data. So now if we look at the data from those shear experiments, what you can see is that for the contacts, we have a very strong alignment in the horizontal direction. And that makes sense based on what we saw in the videos. The stronger we compressed it first in the X direction, and we saw that the contacts appeared in the horizontal direction. For the normal forces, we see a similar case. The forces are stronger in the horizontal direction than in the vertical direction. And then for the tangential forces, we see this really nice peanut or clover appear where the colors indicate clockwise or counterclockwise preference. And so these are for pure shear data. It's all of the data in the video. So compressing and then expanding and compressing and expanding averaged over that. But we can do better than that, and we can bin it by the strain. So if we take this strain and we increase from low to high, we see again that the anisotropy increases or decreases rather. We go from only the forces appearing in the horizontal direction, and then we start to see some more vertical forces appear, or more vertical contacts appear rather. And so if we plot those peanuts for the contacts from low to high strain, we go from something that's highly anisotropic to something that's more ellipsoidal. So the rank goes from peanut-like to ellipsoidal to a circle. And so the next thing that we can do is do this for the normal forces as well. So these are the data I showed you before. Underneath are the normal forces. Again, we see it go from being a peanut to being more ellipsoidal. And then the tangential forces go from highly anisotropic, a much larger value, and then it decreases with strain. So what we can do is plot the contours of these peanuts as a function of angle. And if we do this, we see that the probability of finding a contact as a function of angle varies sinusoidally. That's good. The next thing we should do is do the same thing with the normal forces. They vary in the same way. And the tangential forces vary as well. And then the next thing that I can do is change the strain. So I can increase in strain. And what you can see is that the amplitude of these sinusoids decreases generally. So strain going from low to high and in purple to green. And so what we can do is fit a sinusoid according to these Fourier expansions and plot those, because again, we're interested in how those anisotropies change with increasing strain. And in doing that, I can plot the anisotropy for the contacts as a function of strain. And what I want to point out is a couple of things. The first is that they all generally decrease with increasing strain. And the other thing is that the amplitude of the contacts anisotropy is generally double than the normal forces. And then the tangential forces are about an order of magnitude less. This tells us that the tangential forces shouldn't have a lot to do in this sum. And so remember, we were trying to map the macroscopic friction coefficient to these anisotropies. And what we end up doing is, if we go back to that data that I showed you before, if we plot the sum of those anisotropies on top, we get really excellent agreement with no fitting parameters here. And these are averaged over all of these different data. And I can do this for the pure shear case, as well as the uniaxial case, where we can see an increase and then a decrease in our overall shape, as well as the biaxial compression. So what this tells us is that this matches for the data. The anisotropies tell us about the macroscale friction. But I want you to think about that annulus that we talked about before. And so this works really well. These are beautiful data, and it proves the stress-force fabric relation in real data. But we can do better than that, because we can go back to this annulus that I showed you before. I'll play the video again. And what you can see is the force chains appear and then begin to fluctuate with time. And what we can do is map the macroscopic friction coefficient as a function of rotation or strain. And you can see that initially it decreases. We see that initial strain softening, and then it starts to increase again as it approaches a steady state. And what I wanted to point out here is that even though we're in this steady state, it's actually quite dynamic. There's at this data point corresponds to this image here, which has a lot of force chains. Just a few frames later, just a little bit of rotation later, it goes through a slip event, and we have very few force chains. So even though we've approached steady state, it's far from static. And if we map the anisotropies on top, we get this, it matches almost perfectly. We get this really beautiful agreement. And so that tells us that really the macroscale friction is an indication of how much anisotropy is in our packing. And it maps it even through transient or intermittent behavior. And one of the questions that we were really stuck on was like, how does this work so well? It comes back to this paper by Lee and Yu, and what they essentially do is just equate two sides of this, or it takes two variations of the stress tensor. And in their assumptions, there's no dependence on loading history. And really the only assumption is that the packing has to be in equilibrium. So this wouldn't work for an incredibly dynamic system. And so to conclude, the anisotropy tells us about macroscale friction in granular materials, and the stress force fabric relation works for so many different loading histories and conditions, even beyond the static. And with that, thank you so much for listening. I'm happy to take any questions. My email is down below if you'd like to contact me.
Thank you so much, Carmen. That was fantastic.
Thank you.
And we are open for questions now. Please feel free to either unmute and ask your question or type it in the chat and we can ask them for you.
I'll start with one, which is it intuitive, or is there an intuitive reason why the anisotropy should go down as the strain goes up? Because I would have thought the opposite.
You can imagine, like, as you're compressing it in one direction, eventually you're going to get a point where you start to see grain rearrangement, and then you're going to get contacts forming with the neighbors above and below it, rather than just the neighbors side to side.
Oh, so like the linear response is anisotropic, but then once you have rearrangements, it goes toward isotropy?
Yeah.
Okay, interesting.
I had a question regarding, actually, there's a question in the chat, and I will actually go for that first. Okay, so the question is, there were some experiments whose friction seemed poorly predicted at low shear rates by the stress force fabric relation. Is there some way to understand why those experiments did not match this theory as well as others?
Oh wait, I need to read the chat.
Maybe if the speaker wants to unmute and explain the question, that also works.
Hello, can you all hear me? Sorry.
Yeah.
Yeah, go ahead.
Yeah, can you go back a few slides? I forget the exact number of the slide. There, yeah, this one, yeah.
This one?
One forward, please, yeah. Yeah, if you I'm curious about this figure on the right, as I guess, as well as the one on the left. You know, for example, this pink experiment on the right.
Yeah.
Has I guess a low friction. If you look at the pure shear case on the right, and then I guess the bottom most set of points that are pink,
Mm-hmm.
they don't seem close to this line.
Yeah.
So I guess I'm just wondering, I mean, what's so accursed about these pink dots that they don't fit the theory?
Yeah, and I think at the end of the day, it just comes back to that these are a relatively small sample. I think if we took more data, it would eventually fill in because these ones look a little bit erroneous in terms of there's a gap between them. I also used all of these data to fit the anisotropies. So I suspect if I did each one independently, we would get a much better agreement with each track, if that makes sense.
Okay,
similar to the annulus data.
Yes, I guess, okay, thanks. I think I understand, just to be very clear. So I guess you're saying that, if you took the pink experiment and the cyan experiment and whatever, all the ones in this plot, and you looked at those three magic histograms, and then that is where this sort of fit came from, or whatever, this prediction came from, the A plus AN plus AT. And then, so you're saying that perhaps the statistics of pink were quite different, and so maybe they don't.
Exactly.
Okay.
Such as the cursive granular experiments.
No, I mean, it makes perfect sense. I think these are very good fits. I just want to understand these outliers a little bit more.
Yeah, absolutely.
Thank you for the great talk.
Yeah, thank you. We did check to make sure the first packing that Ephraim made, that it wasn't a weird one. Because when humans make packing versus nature makes packings, can sometimes be very different, if that makes sense. So these are all made by rearrangements of the grains rather than someone going in by hand.
Okay. Yep. Thanks.
Thanks for the question.
Okay, so there's another question in the chat asking, is this, and perhaps what if yes, is the relation of what you presented to percolation networks?
That's to be determined. That's the next step for this project. Great question. We're working on getting the rigidity percolation and like playing the pebble game on these data to see if it matches at all or not.
I have a question sort of related to the one you just answered regarding, the match or the mismatch between individual realizations of these granular experiments and the low order prediction, theoretical prediction in this sort of sum rule that you have.
Mhm.
So you mentioned part of the variability is preparation and protocol dependence and also potentially size of the system. So if you were to work with a larger, either experiment or numerical experiment, if one were to hypothetically do a larger system, is there a sense in which you can also understand this spatially? So you're doing these histograms, rather than doing it over the entire system, can you take sub-samples, sub-windows, and ask how spatially accurate, can you have because the whole system, the whole pattern of force change is extremely heterogeneous, and you might have local effective on mesoscale friction, which is higher in some regions and less so in other places. And can you predict slip events?
Yeah, so currently to be done, we have binned the annulus data by whether it's into thirds, so strong shear band, weak shear band, and then not in the shear band. And it seems like the prediction still works, and I'll pop ahead. So this is an old slide, but we can look at inside the shear band by plotting these three. So we bin it by shear.
Yeah.
And it seems like sorry, these are rough slides. Left is inside strong shear, middle is mid shear, and then outside is not shear and not in the shear band. So inner to outer, left to right. And it seems like it works regardless.
Wow.
Yeah. So the next thing that we want to see is, can we detect angular shifts?
Yes.
As maybe it goes through a slip event. That's something that I really want to look at next once I have time to do that.
That would be very cool. And the friction coefficient you wrote as a ratio of shear to pressure, so which is the conventional sort of Coulomb static friction view. But dynamic friction, especially when you have in this continuous motion in your annular situation, doesn't have to be simply. It could have rate dependence. It could have dependence on the shear rate and on top of the static shear component and the pressure component. Is that something that you've investigated? Is that something that you can use as a way to also now tease out further axes of the structure function relationship that you're already exploring? Yeah.
I mean, even inside of the annulus, we should have different shear rates, right? Because it depends on how far out we are. So I think tuning to that would be really a good way of going with that. And then, of course, we can rotate the annulus at different rates.
Yes.
Just as a reminder, though, in the video, it's sped up by about 25 times. So it is still quite slow. It takes about 2 hours to rotate it a full 2 pi. But I know previous members in our group have used the annulus to measure at different shear rates as well. So it's
I actually wanted to ask about that speed. Sorry, cut you off.
Yeah, no, go ahead.
Oh, so presumably that you chose that slow speed because faster speeds had something else happening. It wasn't enough time to get to mechanical equilibrium. Is there a threshold for where you start seeing the kind of dynamic friction that Suraj is talking about?
To be honest, I chose this speed because it kept up with the frame rate of our camera.
Oh,
It was
okay.
like a good level of speed for the camera's frame rate.
Okay.
So we can go faster, but we would lose more of the rearrangements
I see.
of the
Okay,
force
thanks.
chains. But we can definitely go slower.
I mean, is it your expectation that there's a good separation of time scales where if you did speed it up by a factor of, 2 to 5, you would get the same dynamics, the same rearrangements?
I think so.
Okay.
I think so.
And is there, do you know sort of at the macro scale for these materials, what are like the Coulomb friction coefficients, the static and kinetic friction coefficients?
I mean, when we put it through like the Pebble game, we use 0.3 as our standard particle scale friction. We're working on an experiment right now to see how much it varies between particles. Because friction, you can imagine that the friction between grains really depends on all the little asperities between these grains. So even though they look smooth, there's actually all these little bumps. And what we're trying to see is if we can detect how much those little bumps change. Or like, so we could do AFM on the surface and then see like this particle had a higher friction coefficient compared to another smoother particle, and how much variation we should expect inside of a granular packing like this. And then if we should be using 0.3 or whatever we've measured, or if we should be really using a distribution to have a better understanding of the particle scale friction.
Right.
Yeah. I think there was a question. Have I considered using my grains as components of a regular 2D Ising lattice? I have not considered doing that. I think I know that there's definitely been people who have used not Ising, but they've used electrostatics to try and model areas that are soft and areas or rigid or floppy inside of a lattice. I haven't fully read that paper, so I can't comment on what they found, but they try to do a similar mapping to like as you would do with thermodynamics. So rather than mapping to thermo, they mapped to electrostatics.
So can you make the particles rougher because I noticed that the alpha, as you said, the alpha T was very small. So is it possible to go to a regime where it becomes large?
Yeah. Something that Karen, Dr. Daniels, and I have talked about is maybe having geared particles rather than smooth particles. That would definitely increase the friction. The problem is that really at this point, any shape other than a circle, we can't solve the force vectors for. So it's kind of this catch-22. Like it would be really cool to increase friction, but we'd have to do it with surface roughness rather than or like with texture rather than surface roughness.
More questions? Okay, maybe let's stop the recording for now and then continue with questions.
Oh, there's another one.
Yeah.